Hello everybody, I'm Vincenzo, here's Tim, here's Ralf, and the title of the presentation, as you can see, tries to resemble pulp fiction, and this is the reason why we are dressed this way. So this has also a meaning during the talk, because we will see that Ralf is going to solve some of our problems like the wolf does in the film, and Tim is less tempered than me, so as a way to automatically find gadgets when it comes to return-oriented programming exploitation. So let's just start. So I will basically do the boring part of the talk, the introduction and the overview, and then Tim will explain the algorithm to find gadgets, and Ralf will talk about how to chain gadgets together by the means of a compiler. Then we will show you some fancy demos, and we will hopefully discuss with you further works. So this is like something obvious to say, but if you ever try to write an exploit with some non-executable page protection, some non-executable page protection mechanism, you know that you're basically not having much fun trying to find a way to evade this countermeasure. So in the last few years, there were a few research on how to evade this thing, because nowadays it's really common to have non-executable pages type of countermeasure. Think of, I don't know, DEP on Windows, the non-executable bit on Linux, and you have code signing on iPhone and similar things on other mobile platforms. So basically, the way you would go about having a working shellcode in those scenarios is by using return-oriented programming. So basically, return-oriented programming, the entire point of this talk came out because of two reasons. The first one is that Tim had to graduate, and the second one is that I and Ralf were trying to write an exploit for pawn-to-own. So as you know, the iPhone, as I said before, so the iPhone has something called code signing that is basically a non-executable protection, a non-executable page protection type of mechanism. And so what we found out while writing the exploit for pawn-to-own was that it took us a while to actually find all the gadgets, chain them together manually, and then doing the debugging. And since in the meanwhile Tim was working on his thesis, we tried to combine both things. So let's start from the beginning. So the technique that we're going to explain today, the algorithms in theory can work, like not in theory, can work on every architecture and on every operating system. In this specific talk, though, we will show you how to use them exactly on the iPhone. So when you try to write an exploit on iPhone, you have to face at least two problems. The first problem is code signing. And the second problem is sandboxing. So as I said, code signing can be solved by using return-oriented programming. And as for sandboxing, in our specific case, we were apparently lucky because there was a bug in the sandbox policy of mobile Safari. So we were basically able to dump the SMS database of the phone. Probably not all of you are familiar with iPhone and with how code signing works. So if you write an application for the iPhone, you have to upload the source code to Apple, which will basically, what happens is that Apple will sign your code with their private key, and the kernel, before executing your code, will verify that the executable page are correctly signed by Apple. So, so this is basically a way to have a non-executable page in the process address space. just one thing before continuing the talk. Especially in the past, there were a lot of misunderstandings about exploit on iPhone because there were some bugs in the way code signing was implemented until iPhone 2.0. So basically, you were either able to evade code signing, or by using a jailbroken phone that that doesn't have code signing enabled, you basically didn't have to care about code signing and therefore non-executable pages. Instead, for point-to-on, we really needed to write an exploit for a non-jailbroken phone. So this was a bit harder. So the way, so to get back to code signing, the way code signing works is you have some rules to follow. So the first rule is that if a page has write permission in memory, it can't have executable permission. So you basically cannot change the permission of the page, put there your shellcode, then change the permission back and try to execute the shellcode. Then you can't have any executable pages on the heap. And finally, as I said, only a signed page can be executed. So usually, the way you solve this problem is, as I said at the beginning, return-oriented programming. So you can think of, so in this picture, we have an attacker-controlled buffer and then a sequence of instructions that are basically executed when the exploit is launched. So the simplest way to look at return-oriented programming is that the attacker-controller buffer can be compared to a crafted stack. What you will have on this stack are addresses of instruction in the text segment of libraries or domain executable. And you will then have a bunch of variables that need to be used by those gadgets while they run. So what you're trying to do here is, okay, get a few different gadgets, chain them together so that you're able to have a meaningful payload. And what happens basically when your shellcode is first executed, it will at some point reach what is called a return sequence. A return sequence basically will pop the next instruction pointer from the stack. And this way you're able to continue the execution using your payload. So return-oriented programming basically consists of three parts. Find the gadgets in the libraries or in the main executable, and then chain them together to form a payload, and finally you want to test the payload on your target. So let me just say one thing is, and on most mobile platform nowadays, you don't have address space layout randomization. So this means that you can, you can basically find gadgets in every library and in every main executable in the address space. This makes things way easier for us because we have lots of available gadgets to use. So now Tim is going to explain how to find gadgets in a given executable, and then Ralf is going to explain how to chain them together, and I will finally show you how to test your payload. So Tim?
Yeah, hello everyone. I'm going to go over the part where we're actually going to talk about finding the gadgets and executables that are linked to the binary which we want to exploit. And we want to do this in an automated fashion. So the first thing I'm going to talk about is that we need a goal definition to what we actually want to achieve with this automatic gadget finding. Then I'm going to motivate the whole thing so that we all know, okay, it's not the only thing, the iPhone, that we want to exploit here. So we have more motivation than only owning an Apple device, but also we want to own other devices of other vendors as well. Then I'm going to explain what strategy we are going to use to achieve this goal and go over the steps which follow sequentially after that in short detail so that you all know which path are we going to take. And then I'm going to go in algorithms into the details of this strategy so that we have the possibility to see what kind of algorithms we are going to use to actually find the gadget automatically in the binary. Then there is going to be like a short section over the results where I'm going to explain what the results of the automatic gadget finding are and how they can be used later on from the compiler that Ralf has written. And then some ideas of further improvement and how you could like make this automatic gadget finding better in the future will also be talked about. Okay, what is our goal here in automatic gadget finding? What we essentially want to do is we want to build an algorithm which is capable of locating gadgets within a given binary automatically without major side effects. And side effects here are a very important issue because we use a different approach on gadgets than normally in return-oriented programming have been used in the past. Because what we are looking for essentially is that we use instruction sequences completely to already fulfill the complete operation of one specific gadget. And we are not using single instructions before return to achieve this goal. We are also not looking at the binary itself in a raw format, but we already use like the disassembly of the binary and original functions, so that we can use this representation of the binary to find instruction sequences which are not unintended but intended in the binary already. So what's the motivation to do this? We have like a whole lot of binaries, a whole lot of devices that today use ARM as their major platform to build upon. So iPhone is only actually one of them. And as we are friends of little spirits on devices that keep us from keep us having access to them, even though the owner or the vendor might not even want that, is kind of like the goal of the whole thing. So we want to be execute our code in the presence of non-executable protection, like Vincenzo already said, aka the non-executable bit, or write or execute software protection, and when the code signing of binaries is enabled, like they have shown on the pwn2own contest at Cancer Quest. But to make this very, very clear, return-oriented programming is not a technique to in any way evade ASLR. So if there would be a platform which completely randomizes all the binaries on each start of the binary and each crash of the binary and the restart of the binary, then return-oriented programming, because it relies on static addresses in the binaries, will not work in any way. So what's the strategy to actually achieve this goal? As I said in the goal definition already, what we want to be able to is to build a program from parts of another program. So what we look at is the executable of the binary itself, and we are looking at the library of the binary itself, and take the parts that we need for our program in the binary from those sections of the program. These parts are named through the convention of return-oriented programming gadgets, but are kind of like only instruction sequences if you look at them in a general way. So a gadget is then a sequence of usable instructions that you can use for a specific operation, like A plus B, or like a pointer increment, pointer decrement, or memory dereference, or something like that. And we have defined a term which greatly enhances the normal return-oriented perspective on which instructions can end one of those instruction streams. And we call this instructions free branches. And if you have a small insight on the ARM architecture, then you know that you have a whole lot of arithmetic instructions that are able to influence the program counter, even though they are not a return instruction or not a call or a jump in any way. So we kind of define the free branch instruction as an instruction where, given an instruction sequence that we execute, we are able to influence where this free branch instruction will let the control flow continue the execution within the binary. And yeah. Also, we need to locate useful gadgets. As I already mentioned, most of the gadgets have side effects. We need to use only useful gadgets in the set of all possible instruction sequences which are available in the binary. And therefore, we select only the simplest ones of them because we want to not have the problem that given an instruction provides a useful operation for us, like an addition of 2 registers, we do not want to have this instruction sequence do other calculations or performs memory reads or writes, so that previously executed instruction sequences where operations which we intended to provide the results of those will be overwritten. And another major point of this complete work is we want to be really platform independent. So we're not only aiming at ARM like we discuss in this talk, but we are aiming at all platforms that you can imagine. And therefore, we use the Ralf meta language, which is a platform independent meta language that I will discuss with you now in short detail so that you have a basic idea what you can do with it. So what's Ralf? With Ralf, we have a meta language which we translate all native instructions into. And the Ralf meta language is a small RISC instruction set with only 17 instructions, which we're never going to put on any silicon, but we have an interpreter for. And what we do with this is we take an instruction from any native instruction set and substitute it with a graph of Ralf instructions. And therefore, we have a platform-independent representation of any instruction that you can find on all of the architectures that you might think of. So basically, we have a whole bunch of arithmetic instructions. We have some bitwise instructions and logical instructions. I think arithmetic and bitwise is kind of like self-explanatory, but the logical instructions you see here is, the first one is byte is 0, so that you can check for whether there is a 0 in one register or not. And the other one is the jump conditional instruction. Then data transfer instructions, so we have a load from memory, store from memory, and a store from register to register. And other instructions like NOP, UNDEF, and unknown. And there's an interesting story about the UNDEF instruction, which actually was not originally intended to be in the Ralf instruction set. But due to the fact that some instruction sets like x86 have the behavior that some instructions might undefine flags when run in certain conditions, you need to have this undefined flag to be able to have the same results after interpreting a set of Ralf instructions and interpreting the original native code which was translated into the Ralf instructions, so that the results of both of the executions are the same for all the native registers on the machine. Ralf is completely a register machine and not a stack machine. We kind of like have an unlimited number of temp registers which we need, because some of the instructions that we translate, sometimes if you think about count leading zeros or count leading ones, and you only want to do it with the small instructions that we have, can end up to be almost as like 60 instructions or something like that for one single native instruction in the original binary code. Ralf and its instructions are completely side effect free. That means each instruction only has effects on the registers which are in the definition itself. So there is no flag setting which happens when a Ralf instruction is executed. Flags are completely modeled as registers would be also. What does Ralf not do? We're currently not handling any exception code. We do not do any floating point. And we currently have no support for 64-bit instructions. We do, though, handle 64-bit memory writes, loads, or arbitrary length of that, but 64-bit instructions are not yet in the Ralf translators. So why not? Basically, for a language that is primarily aimed to provide an offensive researcher with the correct tool set to do anything useful, you kind of like have not that much. I currently know of nothing, know of none, floating point instructions which you can effectively use to trigger any kind of bug. Maybe the audience knows more than me, but basically that's it. The no exceptions kind of like comes from that the exception handling and platforms has to be treated architecture independently as well, and we have currently not implemented that yet, so this is one of the further improvements which we can do to the RILE instruction set. So coming back to the original topic of the talk, after introducing you to the RILE instruction set, we're going to now go over the algorithms which are needed to find gadgets in the binaries automatically. We have divided those algorithms in basically 3 stages, so that in stage 1 we collect all the data from the binary which we need for later processing. And in stage 2 we merge this collected data to have it in a state where we can later interpret what actually the contents of the data we have extracted are in a useful manner. And in stage 3, we locate the useful gadgets which we are actually looking for in this merged data. So let's dive right into the algorithms of stage 1. What is the goal of the stage 1 algorithms? First, what we need is, we thought of a way to represent the instructions in a way so that a sequence of instructions can be usefully puzzled together later on. Therefore, we chosen to use binary expression trees which we extract from the native instructions present in the instruction set of the target architecture. And you can see here on the left what a basic binary expression tree looks like. It's just you have nodes and they are connected in a binary tree form, and all leaf nodes are operands and all non-leaf nodes are operators. And in this specific case, you add the register R0 to the immediate value of 15. Also, due to the fact that we're not aiming at having single instruction, then return, single instruction, then return-oriented programming, because we think that the overhead of having all those context switches and having like the huge blow-up of stack space that we need for that, we are looking to extract path information from the disassembled binary in a manner so that we can execute instructions sequentially on the path and then use those sequences of instructions to execute the gadgets in our binary. We do this in the following way. For the expression tree extraction, we have a handler for each possible RILE instruction. Most of the handlers are very simple transform, like I showed you already. The addition is just, you can just simply map from the RILE instruction into the expression tree. But for some of the RILE instructions, it is a little special, because for a store in memory, you might have a register or register plus offset to actually address the memory location you have in memory, and you do not want to override this information later on anymore. Therefore, you need a special handler that the uniqueness of this memory store is always kept. We use some kind of SSA to do that. Yeah, and the JCC instruction is the jump conditional instruction, which needs to also be treated specially, because in the case of a jump conditional, we have to treat the condition in the instruction as well. And we deal with this by, we want to always be representing every instruction in a single expression tree. And you can see this expression tree on the bottom of the slide here. And the condition on the left side is the condition for the true branch, kind of, and op is like the operation which will take part. And we use multiplication once on the left side for the true side and on the right side for the false side, so that we invert the condition and later multiply, so only one of the possible outcomes given the flag as true or false will be eventually present in the expression tree. We therefore do not have to split the expression trees and all of the other information already collected when we encounter JCC instruction in the instruction stream. The path extraction is done through a depth-limited search and is done in a reverse control flow order from the bottom of the binary where the free branch instruction is on upwards until we have reached the limit which we have specified in the depth-limited search algorithm. Currently we use values between 15 or 20 instructions depending on the architecture which we are currently targeting and the compiler which is emitting the instruction sequences. So after we have now collected in stage 1 all the data which we need to be able to merge the data, we're going to now merge the data. So the goal of the stage 2 algorithms is basically that we merge the collected data from stage 1, and we do this by combining the expression trees for single native instructions along a path. As I've told you, we have extracted all the possible paths through the instruction stream in the stage 1, and we can now combine them along exactly those paths. Also, due to the fact that our path extraction was from the bottom of the function up to the beginning of the function, we might have taken a path which has gone over a conditional branch, and therefore we need to determine the jump conditions which need to be true when taking this path. And also, due to the way RILE translators work, they have a whole lot of overhead in the translation, and therefore we have introduced some algorithms to simplify the results so that later the matching in the stage 3 gets simpler. How do we do this? To combine expression trees along for single native instructions along a path, you can look at the example that I've just put on the slide. What you can see here is that we have 4 very simple instructions, where the first instruction basically adds R1 and R2 into R0, and then R0 is stored in R4. And what we have here is that given those 2 instructions are encountered after each other, we use the information stored as expression tree for one single register, and as the registers, operands, are always leaf nodes in the trees, we can combine them together because we know that this register has only been influenced by the instructions we just executed. To determine jump conditions on the path, there is the example in the middle of the slide. Given that we encounter an instruction for which the Z flag in this case must be set false, then we generate a condition and put this into the complete expression trees that we have extracted for exactly this path and save it in there as well, so that we can later see that given we want to execute this specific path, this condition must be in exactly this, must be false or must be true. And therefore we can take paths even though that maybe a conditional branch has been introduced while we found the path. Then we need to simplify the results, and as you can see here on the bottom, a RILE translator, this is the original translation of a load from memory where the register was one of the registers in the ARM register set, which was in the end of the register list that the instruction STM has a whole lot of add 4s in there. If you want to match such a tree, it would mean that you would have a whole lot of nodes where all this information is stored in. But we want to have the possibility to use kind of like a fuzzy algorithm to match those. Therefore, we need to simplify the results to have the trees as simple as possible, and therefore we try to use simple algorithms to simplify the result and just like calculate it. Okay. Now that we have merged all the data along the paths, and we have pretty much for every path that we can execute all the information, how registers, memory locations, and jump conditions are influenced, we can now start searching for the specific gadgets that we are actually aiming to find in the binary. And one of the parts is that we use a tree match handler for each of those operations. So what we basically do is take a tree and try to compare it to some tree that we have earlier defined to see if it matches. I'm going to show a result later on. And then, due to the sheer number of gadgets that, like in a normal library, if you would take libsystem from the iPhone, for example, I think it's like 240,000 gadgets that you can find in there with those algorithms. We only want to select really the simplest possible gadgets that are available to us, so that we don't have to later on in the compiler stage work with so many side effects that on one hand, the compilation time would take forever, and on the other side, maybe never finish, because it's not, because there's no way to compute it. Okay, how does that work? As you can see here, on the left side, there are some of the trees which might be found by the algorithms, and now we are trying to match those with the tree on the right side. And I'm pretty sure that you can really fast spot the match here and have find the tree that exactly matches this operation. That is basically what we do. For most of the gadgets, we kind of like use a fuzzy algorithm so that not all of the leaf nodes have to be of any specific kind, so that we can find more gadgets that essentially, though, do the same work for us. So we are not only looking for a memory store to a register, but also for a memory store to a register plus a small or even large offset, because we can still have the value in the register pre-computed in the compiler, so that the addition of the small or the subtraction of the small offset then gets reversed in effect. Okay. To select the simplest gadget, what does that actually mean? For most of the instructions, like in addition, we have trees that can be arbitrarily complex, but there are also trees which are very simple. And we try to strip down most of the very large and very complex trees, because they are really hard to compile later on because of all the side effects I told you about already. Okay. What I have shown you in the last 15 minutes, algorithms which automatically extract gadgets platform independent for return-oriented programming are feasible and possible. So you can work with those algorithms by using RILE on multiple platforms, and you will get usable results. Also, all the gadgets that in the primary definition of return-oriented gadget, in return-oriented programming, the Turing completeness in this case is satisfied. And also, you always have to think about that searching for those gadgets is very, very platform and very, very compiler dependent. So for the ARM gadget set, which we have tested on various devices, given that the compiler changes, some of the gadgets which are more complex than a normal addition get emitted from the compiler differently on iPhone than they would get on Windows Mobile. So you always have to have the fuzzy tree matching in place there to be able to find everything that you later need to have the Turing complete gadget set. Okay, so what's next? Next, I'm gonna give over to Ralf as Mr. Wolf, and he's going to show you how to combine those gadgets.
Okay, so what's changing gadgets like? It's a lot like playing Tetris with very ugly pieces. Actually, for the iPhone, the pieces are not so ugly, so it's a regular Tetris game. But if you tried, for instance, exploiting something on Symbian and you wanted to build your gadget set just on euser.dll, which is the most basic library that you can have there, it would get very nasty. You'd get very nasty pieces. And playing Tetris by hand with very ugly blocks is not something that we enjoy doing. So where does this complexity come from? So basically each gadget set that you have defines a custom instruction set architecture. So whenever the version of your library changes, or maybe there's a compiler change, Apple has switched the GCC to CLang, you will have a new gadget set. However, we have better scores at piecing together Tetris than this. Nonetheless, it has become difficult in some cases, hence we have decided to bring in some help. This help is Mr. Wolf. So, Mr. Wolf is a ROP compiler for gadget sets with side effects. So, you may wonder why you haven't seen anything about this before. It's interesting. So, there are a number of academic papers on return-oriented programming, but they all consider the case where they don't have side effects because they don't deem that interesting. What we have found is that if you want to automate this process on most RISC architectures where you don't have unintended instruction sequences as you have on x86, you will have to deal with side effects. And hence, we have built the Wolf. So at the moment, the Wolf is only for ARM, but it's about a weekend of effort to port it to another architecture. It's a very basic language that we use, or that you use if you want to use the Wolf. And at the moment, it's kind of a prototype that's implemented in Python. This probably will change in the future if I understand things correctly. So to live with side effects, you have to adapt the language that you program in. So what we do is we give the programmer several opportunities to tell the compiler what he may do, what things he can, like what registers he can clobber. So all of the registers that the compiler is not allowed to clobber, you protect. So the protect statement is given a list of registers, and between two protect statements, these registers will stay invariant, except if they're explicitly modified by the assignments you do in between. The allow read statement gives you the opportunity to tell the compiler which memory ranges are okay to touch for reading without triggering any page faults. And the allow corrupt statement gives you the opportunity to tell the compiler which memory ranges he can actually overwrite, which are basically expendable to you. So you may or may not repair them later. Okay, now operational side. What kind of statements do you have in the language? It's a very, very simple language. So the most important construct that we have is a multi-assignment. So this means that you basically have a tuple of components on the left-hand side and on the right-hand side. You'll see it on one of the next slides. Then we have a conditional goto statement, which you will need if you want to have loops. And this conditional goto statement is very simple. It's a goto if non-zero. So what you pass it is basically a register or a memory location that, if it is non-zero, will trigger a jump to a label. And the other thing that we have is a call statement for interfacing with native library functions. The other two things are data definitions, obviously. You may want to have some of those in your code as well. And obviously you need to have then labels for these data definitions and for the code if you want to make use of the conditional goto statement. So how does one of these multi-assignments look like? This is from the Pwn to Own contest. So this is the payload translated back into our language. This is just one of the statements that is in this. So the full payload you see in the white paper. So this is basically the setup that you do in the registers before you do the connect call. So what you do there is you have 3 target registers of 0 to R2 that will be assigned to first basically a star pointer. So you do a memory read here. So you read the memory at the address socklock, which was where you previously stored a file descriptor for the socket that you opened. Then as a second argument, which goes into R1, you have the data reference to the sock address in that you have defined, and the third is just a constant assignment of the size of this struct into R2. So you will notice this kind of funny thing in between that we use as an assignment operator. This is a very nasty hack because you cannot overload the assignment operator in Python. Okay, a loop is a very simple thing as well. You define the label for the loop. You define a counter. In this case, it's a register. Then we're doing something kind of nonsensical, but maybe pedagogical. So what you do is you assign a range of memory of 1024 bytes to 0, so you just clear a range of memory, and at the same time you compute multiples of the register R1, which is basically going down from 256 to 1, and you compute that in the register R2. So what you'll notice here is that the right-hand side of this multi-assignment contains the computations. So this is how you actually perform arithmetic logical calculations in this language. So all of them will be done in assignments or multi-assignments. Okay, so now we come to the actual implementation of the Wolf. So Mr. Wolf is a very high-level problem solver. He likes to delegate and he likes to have his things done fast. So what we did in this case was we used a tool called STP, with a simple theorem prover, to do the manual work for us. So STP, some of you may be familiar with. It's a constraint solver for problems involving bit vectors and arrays. It's an open source tool that was written by an MIT researcher called Vijay Ganesh, and previously it has been used for model checking, theorem proving, EXA, which is a paper about constructing so-called inputs of depth, and other things in the security community. So what it does is basically you give it a formula in this theory of bit vectors and arrays, and STP will tell you whether this formula is satisfiable or not, and if it is satisfiable, it will tell you an assignment. So an STP formula is just a bunch of assertions in this theory, which is called the quantifier-free theory of arrays and bit vectors. So this is actually, there are a number of theories that you can build these solvers for, and this is one of them. So there are yearly competitions for these. It's called SMT, Satisfiability Modular Theory, and this is one of the simple most that you can deal with. So a simple example in this STP language would be just an assertion for a simple formula that just involves additions and multiplications. Obviously, that's very simple. Usually, you will have much bigger things. So this is just 10 different variables of 4 bits each. So what we do is we translate the expression trees that Tim has spoken about into STP formula in the algorithm that we use. And I will now give you a high-level description of this algorithm, and I will specifically concentrate on the multi-assignment because compared to the other things that we had to do to get the Wolf operational, the multi-assignments were the most work. So what you do to generate ROP code for a multi-assignment is you first find all of the gadgets that allow you to assign the targets on the left-hand side. Then for each of these gadgets that you have enumerated, you verify that the constraints that at this point have to hold really do hold by converting the gadgets into STP formula, triggering STP, and then if it tells you this is not satisfiable, you just scratch it off the list. Then you go to the right-hand side of your expression, and you do the same thing, but of course there you have to build the expressions and you have to chain the gadgets, so you go from inside out, and you incrementally build this and you get more and more complicated STP formula. Obviously, for each of these steps, you have multiple gadgets potentially that you can use. So you have kind of a recursive procedure where you throw out the gadgets that cannot be used in each recursion step. Now, when you're done with that and you have the left-hand side and the right-hand side, you connect those two. Again, you have to verify that the constraints do hold. Obviously, if it's just a constant assignment that you do, that's trivial. So you don't have to do anything in the component on the right-hand side. It's just the left-hand side that you consider there. Now, you may ask yourself, why do we have this multi-assignment? So the reason for that is that we wanted the compiler to have flexibility. So what actually happens is that you can perform these multi-assignments in different orders. And the order is randomly chosen. If this order cannot be, if like a ROP shellcode for this order cannot be built, what the compiler does is it just chooses another permutation of the assignments and triggers the procedure again. So why is that necessary? So for instance, you may have the case that you always have gadgets that whenever they compute an addition into the register R0, clobber the value R1. On the other hand, you need to assign the value, the register R1 to a value. So the programmer goes, and if you didn't have a multi-assignment, first assigned this, R1 and then R0. Then this couldn't be satisfied. With multi-assignments, you can give the compiler the freedom to choose this for you, basically. Okay, so some notes on the chaining algorithm that we use at the moment. So it obviously will use registers, but also memory locations as scratch for temporary results. The multi-assignments give us the freedom that we need. So without the multi-assignments, some of the demo programs that we have actually would not compile with the gadget sets that we have. But also, it is possible that the algorithm will fail, or let me put this a little bit more mildly, it will tell you that the program cannot be compiled as you've written it because the gadget set is insufficient. So this can actually be solved in a number of cases. One of them is for you to rewrite the program then, and maybe it works in a different way. The other way that we could explore here is to have a term rewriting system that transforms some of the equivalent statements that you can have. For instance, if you have a multiplication by 2, you could just as well transform it into an addition of the same value. But we have not done that part yet. Okay, so I will now hand over to Vincenzo, who will tell you about how to test the payload.
Okay, so Tim and Ralf have shown you how to basically create the payload by first finding the gadgets and then chaining them together. So now let's say that you have your payload and you are still targeting the iPhone. There is the problem of testing the payload. So one can think that testing the payload on a jailbroken phone might be an option, but in reality it's not. Because first off, basically on the jailbroken phone, you have no code signing. So a jailbroken phone is not like a non-jailbroken phone. So if reliability is your primary concern, then you should avoid testing your payload on a jailbroken phone. On the other hand, you can use a debugger on a jailbroken phone like GDB, whereas on a non-jailbroken phone, this turns out to be impossible. So another way you can go about it is to use a developer phone. So basically, it's a phone enabled with a developer certificate. So the idea is pretty simple. You have a simple test application that tries to reproduce a return-oriented programming scenario. And there's still a problem, though. The problem is that the sandboxing policy for the testing application will be the strictest one you can find on the iPhone. Because I forgot to mention this at the beginning, but basically on an iPhone, you have different sandbox policies depending on the application. So the App Store application are the one with the strictest sandboxing policy, but it's very likely that you are instead targeting some other type of application like Mail, Safari, or even some daemons which have either a different sandboxing policy, or in some cases they don't have a sandbox at all. So still with a developer phone, you can try to verify whether or not your payload is correct, but probably the kind of thing you can do with your payload really depends on the target application. So, but anyway, this is like the closest you can get to reality. And also, if you have a developer phone, you can use the Xcode debugger to try to get some more information about the payload itself. Because otherwise, like what we had to do for Pwn2Own was debugging the payload using the crash log from iTunes, which is really not fun. So, the plan for the testing application is really simple. So you basically allocate a buffer on the heap. You put your shellcode inside this buffer on the heap, and then make sure that the stack pointer points to the attacker control buffer, and you basically execute the payload and restore the execution so you can try it multiple times. And now we're going to show you a simple demo about on testing a payload on a developer phone, and then we will discuss briefly the future plans that we have for return-oriented programming. Okay, thanks. Okay, so we're going to show actually two different things. The first thing is a payload. Well, sorry, a payload like the same payload we use for Pwn2Own, but written in the language that Ralf created for our compiler. So, Ralf, do you want to briefly explain it, or shall I do it? Okay. So basically, like the payload was a file stealer payload. It was really simple. You have to basically open the file that you want to steal, then create a connection to a remote host and send over the file. So as you can see here, we are basically able both to call library functions and do other kind of operation as well. So first, like we are opening the function, we pass the arguments to open. We call the function, and then we make sure that the return value of open is protected, so it's not overwritten by other gadgets. And then we call socket, and once again we are protecting the return values of socket, and we connect to the remote attacker controlled host, and here we are mapping the file on in memory, and then we basically send the file to the attacker, and here we are sending the file to the attacker, and then we basically shut down the process. So So this is like the point of this demo is to show that it's actually feasible to write like complex payload using the language that Mr. Wolf understands. So for a problem with the sandboxing policy, being that our our testing application runs with the sandboxing policy of an App Store binary, we are not going to show you this payload, but we will show you a simple vibrate payload. So. So let me just create a network for the phone. Okay. So basically what we will do now is to use our test application to make sure that this payload actually is actually correct. So this payload is really simple. It's basically just call a function called audio services play system sound that basically make sure will make sure that your phone vibrates, and then it will exit, and that's pretty much it. And so this payload compiled looks like this. Okay, so like something like this, and now can't remember. Okay. Let me just. Sorry, I forgot to connect the iPhone to the test network before. Okay, this is acquiring this IP address. Okay, so okay. So we run on the iPhone the test application, and now if everything goes according to the plan, can you hear it? Okay. So this is basically how we test the payloads, and so enough with the demos. The future work. Okay. The future work. So, as Tim said, at the moment, the algorithm for finding gadgets is really dependent on the compiler and on the platform. What we are planning to do is to port port the gadget, like the gadget finder, to other architecture like x86, so that it's possible to use the same algorithms for like Windows, Linux, OS X, and so forth. And a problem related to this is that we need to find to create like an abstract language to describe the gadgets, because at the moment they are, as I said, really architecture specific. So what we want to have in the future is a way to generically describe them, so that we don't have to have a different like interpreter for each architecture. And the third problem is try to avoid hard to solve problems by the constraint solver. So what this means is we want to find an algorithm that will basically select the gadgets so that they are the lowest possible amount of side effects. This way, the constraint solver will not face really hard to compute constraint to be satisfied. And finally, since on like x86 operating systems, and possibly in a near future on mobile platforms as well, we're going to see the address space layout randomization. What we want to do is to make sure that our tool is kind of able to circumvent this. So what we're planning to do are mainly two things. The first one is verify whether or not it is possible to actually create meaningful payload without having Turing completeness. The reason behind this is in some address space, there are some specific libraries that are not randomized. So if we are able to create payloads just by just having a few gadgets, then we don't need Turing completeness, and unless the entire address space is randomized, the tool is still usable. And the other thing that we plan to do is to make sure that our tool is able to generate what is called an egg counter, return-oriented programming egg counter. So basically an egg counter is responsible of finding other gadgets in memory, so that you can basically form the entire payload in memory. So that's pretty much what we plan to do in the future, hopefully. And thanks for your time. If you have any questions. No questions? No questions?
I think up here you asked what kind of library we used on the iPhone, right?
It was WebKit. Yeah. Yeah.
How big it is? Yeah, you saw the compiled payload on the screen, right? I don't know.
I think it was about 1,040 bytes, if I remember correctly.
Anybody else? Yep.
How long did it take for the wolf to find
Ralf?
Okay, the wolf is actually the compiler, so it doesn't locate the gadgets. Are you asking how long the compile time for the gadgets are? Okay.
So the compile time really is, it can be improved at the moment. So it's on the order of minutes, usually per statement. But this is because it's kind of an ugly construction. I trigger STP externally every time. I write to temporary files and all that kind of things. So this can be improved. Also, if we get the number of side effects minimized up front, this will improve as well. But to be honest, compile time isn't an issue in my opinion, at least. I can do something else while the compiler is working for me. As long as it's correct and it is finished in a finite amount of time, it's okay.
Yeah, basically, you always have to think that doing this work is all done because you can spend your time with doing more useful things than going through IDBs and searching for specific instruction sequences and putting them together later on. therefore we did that so that we can spend the time with cooler things to do than this.
Anyone else? Nope. Okay. Thanks a lot for being here.